Hello, I'm Ruiqi. I am a Ph.D. student at UC Berkeley, co-advised by Dan Klein and Jacob Sternhardt. Today I'm going to talk about scalable oversight, a topic that I have been working on during my Ph.D. As AI systems do more and more difficult tasks, we need to figure out how to validate if they are correct without spending a lot of money. But before diving into AI systems, I want to tell you a story about a guy who almost faked his way to a Nobel Prize. Back in 2000, there was a scientist, Yang Shun. He published a really famous paper claiming to have made a big discovery. The reviewers thought that everything looked good, so it got published into Science. Then Yang was super productive during the year. He wrote like one paper every 8 days. For these papers, he was given a lot of awards. But here's the twist. Nobody could reproduce the results. A year later, it turns out that Yang was just faking results all along. So what went wrong here? I think there are two factors. First, the reviewers couldn't really check if Yang was right. The scientific process is complicated, and reviewers can't catch everything. Reviewers' validation does not equal to being actually correct. Second, Yang was getting rewarded just based on peer reviews. Putting these together, Yang is incentivized to fake plausible sounding discoveries rather than doing actual science. And here's my concern. If we are not careful with language models and AI systems, they will end up acting just like Yang. So let's look at the same two factors with language models. The first factor here is that we often can't tell when they are wrong. This actually happened to me 3 years ago. I asked Claude about US elections, and it told me, I Googled and read this USA government website, there are currently 270 electors now. If you know anything about US elections, that's completely made up. The model even lied about doing a Google search when it couldn't even access the internet. But I totally believed it. I didn't know much about the US election systems at the time, and the model sounded so confident. So my validation does not equal to what's actually right. The second factor here is about how we train these models. When a model says something we think is right, we reward it. When it says something we think is wrong, we penalize it. Now put yourself into the shoes of the language model for a second. What is it going to do? It's going to try to sound really convincing even when it's totally wrong. In our paper, we show that under pretty normal conditions, models naturally learn to make everything sound plausible and convince humans they are right, even when they are completely wrong. This isn't just some theoretical results, but also appears on news headlines. Breaking: Lawyer used ChatGPT in court and cited fake cases. That actually happened in real life. The model made up some fake legal citations that sounded legit to the lawyer. The lawyer failed to validate, and now he is facing sanctions. That story is from a few years ago, and I bet things have only gotten worse. The reason is that we're asking these models to do way more complex stuff right now, like finding patterns in data, writing complicated code, or even helping with research. And if we go back to that first factor, our validation will increasingly diverge from what is actually correct as the task gets more complicated. Let me elaborate where this is heading if we cannot get validation right. Imagine this futuristic scenario. It might be 10 years from now or 100, depending on how fast you think AI is advancing. At some point, these AI systems will get really capable. You ask a question, how does gravity work? And it goes off, does a bunch of research, and hands you a 100-page paper on general relativity. How do you validate it? Peer review is already hard for human papers, and scientists have spent over a century validating general relativity. If we cannot properly validate AI systems' output, we can't tell if it's a true genius like Albert Einstein or a fraud like Yang Shun. So if we want AI systems to tackle really tough problems, we need to figure out how to do validation properly. Here's my research goal in a nutshell. I want to enable language models to do really hard tasks, like finding patterns in data, writing software, or helping with research. But to do that, we first need to solve this validation problem. We need to know whether they are correct or not. This has not been a very popular research before because models weren't good enough for validation to be the main problem. But now the models are getting more capable and validation has become the key bottleneck. So that brings me to my title, Scalable Oversight. This term comes from the AI alignment community. Scalable basically means cheap enough to actually use in practice. And oversight means validation. We want to make sure AI systems are doing the right thing without spending all of our money. Most people are more familiar with the word validation, so I'll stick to this word for the rest of this talk. Note that I'm implicitly assuming that AI systems will optimize against some validation metric. This is currently the most popular and effective way to build AI systems, but there could be other methods as well. Anyways, it's always nice to have cheaper validation, at least for evaluation. Let me explain what I mean by cheap here with an example. Say we have this task, find the students with the most pets. We want the language model to turn that question Q into a SQL program P. For those of us doing machine learning research, we need some way to check if the output program is correct. So we create a validation function V, where V equals 0 if the program is wrong, and V equals 1 if it's right. If you know RL, this is just like a reward or cost function. But how do we get good validation? The programming task is complicated, so you might need to hire 4 expert programmers to look at the program for 2 hours each and decide if it's correct. That works, but it's definitely not cheap or scalable. It uses a ton of resources. The big question here is, how can we create a cheaper validation method V prime that uses way fewer resources? Here are some ideas to cut down resource needs. First, what if we can validate programs by hiring regular people who do not know how to program? Instead of 4 people checking, can we get down by just 1 person? Can we skip humans in the loop altogether and have language models do the validation automatically? Can we shrink the validation time from 2 hours to 30 minutes? These are all ways to make validation cheaper. We call the difference between these expensive methods and the cheaper method the resource gap. To sum up what scalable oversight research is trying to do, we want to create V prime, a cheap validation method that approximates V star, which is a gold standard but more expensive validation. Then to check how good our V prime is, we can compare it to V star on a small dataset where we can afford to use the expensive method. That is the scalable oversight research paradigm, and now I'm going to tell you about 2 concrete tasks where we try to accomplish this goal. The first task is programming, where validation is challenging because it involves abstract reasoning. The second task is discovering patterns from datasets, where validation is hard because it requires processing large volumes of information. For the first task, I will show you how we can develop a method that allows non-programmers to validate whether a program is correct. In the second part, I will show you how we can validate dataset level properties without even needing a human in the loop. Throughout this talk, I will describe a technique called decomposition. We will decompose a hard validation task into something simpler, which we call weaker validations. For example, in order to validate whether a program is correct, we can compose a bunch of weaker validations on individual input-output test cases, which is much simpler. For another example, to validate dataset level properties, we can compose weaker validation on individual data points, which is also much simpler. That is how decomposition works. Once we can validate whether language model output is correct, we can use that information to reject bad samples from the language model and then improve the performance as a result. Finally, note that the work presented here came from 3 years ago, so the specific method will be outdated. However, some general lessons will remain. At the end of each part, I will briefly discuss what are the takeaways that are still relevant these days. Now let's dive into the first part, programming. I will first talk about how to validate programs, and we'll do so by composing weak validations on execution behaviors. Here's the setup. We're given a question Q, and we'll map it to a SQL program P. Our goal is to validate whether the program P is correct or not. Typically, in the current RHF training paradigm, we will recruit experts to read the SQL program P and tell us whether it is correct. However, this process is quite expensive because recruiting experts requires money, and this process could also be quite noisy because experts can also make mistakes. The key idea we'll use today is decomposing this validation problem into weaker validations on return values. This idea has similarities with the programming by example literature. So in this idea, instead of asking people to read the SQL program P, we will ask them to look at the input-output examples. For instance, given the question Q, find the first name of students who have both cat and dog pets, we show people a database where Alex has a cat, Alex has a dog, and execute the SQL program on this database to get a return value Alex. Obviously, the return value is correct here, and this is something that even if you don't have any programming expertise, you can reliably do it. To formalize this, we say that W equals 1 if the return value is correct on this specific database. However, this validation is weak because it only tells you whether the SQL program is correct on this database. It doesn't tell you whether the SQL program is correct overall. So we need to find some way to compose a weak validation to tell us whether the program is correct in general. There is no rocket science in how we do the composition. We basically say the program is probably right if the weak validation is correct on a purple set of databases SDB. In other words, if the program is correct on many databases, then it's probably right. In practice, if you have a purple set of databases, you can execute the SQL program on these databases, get the return value, and then run the weak validation to check if the return values are correct on each database. This sounds very good on paper, but it's not really scalable in practice. A human user is required to carry out the weak validation, and they're miserable because they need to be dedicating their entire life reading databases about cats and dogs. To sum up, we need to carefully pick the set of databases to perform weak validations. Note that nowadays, language models could automate these weak validation tasks. However, it was not quite feasible in 2022. In the next few slides, I will talk about some clever ways to select the databases, and similar frameworks could still be useful in tasks beyond SQL programming. So here's how we select the databases. We want the databases to expose the differences between what is possibly correct versus what is actually correct. Let's say we sample 2 SQL programs from the language model instead of just sample 1 SQL program from the language model. One of them looks really plausibly correct, but is actually wrong. And the second SQL program is actually right. The first SQL program might extract the first name of cat owners, first name of dog owners, and then take the intersection. When I first looked at this SQL program, I was confused about why it was wrong because the logic sounds really plausible. As a result, it will be really helpful to find a database where the return values are different, which would really help me explain why the first SQL program is wrong. Here's an example database that clearly shows the issue. In this database, Alex Pan has a cat, Alex Wu has a dog, so the correct result should be an empty set because nobody has both cat and dog pets. However, if you follow the logic of the first SQL program, there is an Alex who has a cat, there's an Alex who has a dog, and if you take the intersection of them, the return value is Alex. With this very small database, it is obvious that the first SQL program is wrong. We run the weak validation on this database, and the return value is 0. So ideally, we want such databases that can expose the difference between the program that is actually right versus a program that looks right but is actually wrong. However, in practice, such databases are rare because the difference is only exposed when the database has 2 different persons with the same first name. We need a method to search for such databases, and here's how we do that in our work. The algorithm is the main contribution of our EMNLP paper. First, we use fuzzing, where we generate large databases and search for ones where the return values are different. However, we can't present this large database to the user because they don't have time to read the entire database. So the second step is reducing its size by delta debugging. We iteratively drop rows from the database while maintaining the constraint that the return values are different. Additionally, our work extends this to not only tell the difference between 2 SQL programs, but also expose the difference between a large set of SQL programs sampled from the language model. In this case, we optimize the database against the entropy of the return value. As a result, we can use that database to maximally expose the differences between many SQL programs and allow the user to pick out the right one. To recap, we need to validate whether P is correct. We probably don't want the user to directly look at the SQL program P. So instead, we present the user with a small set of databases like DB1 and DB2. And then the user will do the weak validation on these smaller databases. On the second database, the return value is wrong, so we know that V prime of P equals 0. As a result, we compose the weak validation in the blue box to perform the validation task in the red box. Even if the user doesn't know anything about SQL programming, they can tell that the program is wrong. I have covered the first half of the first task, where we compose weak validations on return values to validate whether the program is correct. However, I have just shown you a validation technique. How do we know that v prime is actually useful in practice? Now I will show you how to benchmark validation v prime based on its downstream utility, whether it can improve the language model generated programs. Specifically, we sample multiple candidates from the language model and use v prime to filter out the bad programs. For ground truth, we establish a v star determined by 4 programmers discussing with each other. We evaluated our system on the spider dataset. Typically, when we benchmark the language model on this dataset, we sample only one SQL program from the language model. The accuracy is 59% in this case. However, if we sample 16 different SQL programs, then 88% of the time, one of the candidate is correct. If we had an oracle telling us which SQL program is right, we could go from the accuracy of 59% to 88%. However, we don't really have that oracle, so we will use v prime that we have built to filter out the bad programs. In this case, v prime tells us that the third program is correct, so we treat this as the output of our system. Let me show you what we have found. When we just have an expert looking at the SQL code, they get around 75% accuracy, and they make mistakes because this dataset is hard. If you take a non-expert and ask them to validate a SQL program, they get 0% accuracy. There's no surprise here because they don't understand SQL. Language model alone hits around 59% accuracy on this task, as we have mentioned. Our system that combines language model with non-expert validation reaches 75% accuracy. And finally, remember that the theoretical ceiling is around 88% because we are bottlenecked by the top 16 accuracy. So what does this tell us? First, language model plus non-programmers work better than either one alone. Our approach lets language models team up with regular people to produce something better than either of them could do separately. Secondly, and this is pretty cool, language model plus non-experts match what experts can do. This suggests that language models could empower people without special training to perform expert-level tasks. These results are from 3 years ago. Language model has become much more capable since then, and the exact same algorithm I presented today is probably no longer relevant. In particular, we can replace a human in the loop with an AI system. However, back then, language model could not do the weak validation task of validating return values itself, and we designed the decomposition so that human can provide complementary information. Human and AI will still be complementary in many domains in the next few years, so this takeaway will still remain relevant for a few years. Secondly, it is always important to minimize efforts required for humans, because human time is and will still be valuable and expensive. Finally, we will still live in a world where the top 16 accuracy is much better than the top 1 accuracy, so it will still be useful to expose their differences so that humans can choose among them efficiently. So that wraps up the first part of programming. We showed how we can break down program validation into weaker validations on return values, and then use that to improve what language models can generate. And we did all of this without needing an actual programmer involved, which makes the whole process much cheaper. Now let's talk about the second task, discovering patterns for datasets. Validation is hard for this task because there is just so much information to process from the dataset. So what does it mean to discover dataset patterns? Here are some examples. If you're a machine learning engineer with a training set and a test set, you might want to understand how they differ. If you're selling products on Amazon with 1 million customer reviews, you can't read them all yourself, so you might ask a language model to categorize them. If you're a data scientist at Google, you might want to understand how search queries change throughout time. They might talk about flu symptoms more often, which implies a disease outbreak. For time's sake, I will focus mostly on the first example, discovering dataset differences, but our research applies to clustering and time series as well. I will introduce a new task, discovering dataset differences. We are given 2 sets of text, let's call them SA and SB. Our job is to figure out what's different, what's more common in SB than in SA. In this simple example, the output might be SB contains more sentences than is in English. This is an open-ended task, so there could be many different right answers. For example, it's not in Chinese or is written in English. Additionally, we don't need the description to perfectly separate SA and SB. It's fine if SB contains a Chinese sentence. Now here's a question for you. What is the difference between S8 and SB? The answer is quite simple. Alright, so in this case, SB contains more numbers. It is quite straightforward. Here's another example, but much harder. What is the difference between S8 and SB? Feel free to pause the video and look for the differences yourself. In this case, SB contains more green object. As you can see, this task is quite difficult. Here's another important thing about this task. Even if you know the right answer, it is very time-consuming to check whether it is correct. Imagine that you are an annotator with limited time trying to decide if a pattern is real. You might only have the time to read a few sentences from each set and think, well, yeah, this looks right to me. However, if you have the time to go through the entire data set, then you might realize that it is actually wrong. So why should we care about this puzzle? It turns out that many important applications can be reduced to this puzzle. If you're a social scientist, you might want to understand how Trump's speeches changed from 2016 to 2024, and find that later speeches focus more on government efficiency. If you're a doctor, you might want to compare the patient's feedback for drug A versus drug B. The later might mention feelings of paranoid. If you're really interested in interpretability, you might want to understand what makes certain inputs activate a neuron in a language model versus inputs that do not activate a neuron. There are tons of other applications like this, and in our paper, we cover more than 600 such applications ranging across business, politics, machine learning, and medicine. To conclude, this is a hard but important task. Now I will introduce our method to tackle this problem. I will first talk about how to validate data set level property by composing weaker validations on individual data points. Because we decompose it into something simpler, we're able to make validation cheaper by not having the humans in the loop. Here is a reminder of what our task looks like. We have got SA and SB, and we want to generate a discovery D for their differences. The typical way to validate the discovery D is to hire annotators to check if the discovery is right, or to ask a language model to read the entire dataset. However, humans take very long time, and datasets are usually too big to fit into a language model's context window. So instead, we break it down into simpler validations on individual data points. It's much easier to check whether a single sentence contains a green object than to check an entire dataset. For example, broccoli is a green object, and football is not a green object. To formalize this, we say that W equals 1 if X matches D, and W equals 0 if X does not match D. This is simple enough that even without expertise or much time, we can do it effectively. However, it is only weak validation because it doesn't really tell you things on the entire dataset. It only tells you things on individual data point. So we need some way to compose these weak validations. The way to compose these validations is quite straightforward. We check how often D is correct on SB minus how often it is correct on SA. And this is what it looks like in practice. To validate whether D describes the differences, we will run the weak validation on each data point. We will calculate how often D is correct on each data set, take the difference, and then conclude that V of D is low. However, this is not practical because there's a human in the loop, and that human has wasted their entire life looking for green objects. Fortunately, because checking whether D matches X is simple enough for language models, we can delegate this task to them. We apply the language model to validate individual data points rather than the entire dataset, and we call it W prime. As a result, we can compute V of prime, which is an automatic validation function for the dataset level property. This decomposition is what makes this idea works, because otherwise, the entire dataset cannot fit into the language model's context window. To sum up, we can compose a weak validation in the blue box to validate the dataset level property in the red box, which is a challenging validation task. I have just finished the part about automatic validation. And how do we know that it is useful? Similar to before, we will evaluate its quality by using that as an optimization metric and checking whether the performance could increase by using V of prime. We will sample multiple candidate differences from the language model and use V prime to filter out the bad ones. To benchmark our method, we will compare it to human-validated differences. Here is how we optimize against V prime. We give the language model a prompt. Here are some samples from SA, here are some samples from SB. How are samples from SB different? You can view this as a brainstorming prompt, and this process is similar to how humans can come up with discoveries by looking at data points. The language model will then return a list of potential discoveries. Some may be hallucinated, but that's fine for the brainstorming stage. Later, we can filter out the bad discoveries using V prime. In this case, D3 is the best, and filtering with V prime increases the performance from 24% to 53% on our benchmark where we know the ground truth. Such an idea does not only work well on academic benchmarks, but also on real-world applications. I will present two applications here. In the first one, we use language model to understand language model weaknesses. In the second one, we use our system to understand some cognitive science questions. The first application is about comparing differences between language models. When Llama 3 was released last year, people were excited because it matched Claude 3's performance on Chatbot Arena, but it was unclear exactly where Llama 3 was better. We can turn this question into discovering differences between datasets. For example, SA is a set of data points where Llama is better, and SB a set of data points where Claude is better. Using our system, we found that Llama is better on places that ask open-ended, thought-provoking questions, while Claude is better when there is a technical questions involved. This is quite similar to the expert analysis from the Chatbot Arena team, who spent 2 to 3 days on this question. In the future, we hope our system can automate such analysis. The second application is about cognitive science and human memory. 10 years ago, vision researchers wrote a paper trying to understand what makes image more memorable to humans. We can turn this question into discovering differences between datasets. For example, SA is a set of non-memorable images, and SB is a set of memorable images. Using our system, we found that non-memorable images usually portray tranquil natural scenes, while memorable images highlight emotions or expressions. This matches the expert manual analysis from a decade ago, where researchers spent significant time categorizing and analyzing these images by hand. In the future, we hope our system can speed up the process of scientific explorations. Our work has real-world impact beyond research papers. OpenAI and Transfuse have scaled up our ideas to explain language model neural activity, where they set SA to be a set of inputs that do not activate a neuron, while SB to the set of inputs that activates a neuron. Similar ideas are being applied to explainable clustering, where each cluster gets a natural language description. Anthropic has used similar approach to categorize user dialogue. As a result, they have much better understanding of how language models are used in practice. Finally, Chatbot Arena is using our approach to categorize different styles of language model outputs. This project is from 3 years ago, and what is still relevant now? First, after we have decomposed, we should automate weaker validation whenever possible. In this project, the language model can handle validations on individual data point because it is simple enough. The second relevant takeaway is that we should be willing to use more compute at test time for validation. We run the weak validation on every pair of discoveries D and the sample X, which is a significant amount of compute. However, it is worth it as we see that the results on our benchmark and real-world applications. That concludes our second task. We showed that we can break down dataset level validation into weaker validation on data point, and then use that to improve what the language models can generate. Now let me share some thoughts about the bigger picture of where language model research are heading and future work that I'm excited about. Here is how I think about what's driving progress in AI. Back in 2019, models were still pretty limited. They could check grammar, solve simple math problems, classify topics, or do basic sentiment analysis. Now, however, they are helping writing legal briefs, brainstorming research ideas, doing data science, and handling complex software engineering tasks. I see two major factors driving these progresses: optimization and validation. First, optimization. We will have bigger neural networks that have lower training loss, faster GPUs and TPUs, and smarter language models that are better at accomplishing goals using inference time compute. Without much innovation, we will be able to improve them in the future. Overall, I'm not worried about it. The second factor is validation. We are lucky to have relatively cheap things to optimize against, like predicting the next token on the web, preferences from the users, or clear grading metrics for domains like math and competitive programming. However, as tasks become harder, it is not immediately clear how we can validate efficiently. I believe that validation is important for the future of AI. With good validation and a large amount of optimization, we will do great. With bad validation, however, we will have many silent failures. We will have a lot of things that look good on unreliable validation metrics, but aren't actually good. Validation will be hard and become our bottleneck because they are expensive. For example, it is hard to make sure software is completely bug-free. It is hard to tell if a policy recommendation is actually good, and as researchers, we know it's difficult to validate research papers or checking if the reviewers got it right. Because good validations will likely bottleneck progress, we need more scalable oversight research to build cheaper, reliable evaluation methods. Some ideas I'm excited about involve learning to validate with fewer resources. In this talk, I have shown you how decomposition can help, breaking down program validation into weaker validation on return values, or data set properties into weaker validations on data points. But there is a problem. All the decomposition methods I have shown here were hand designed by me and my collaborators, and that is pretty slow. In the future, I hope language models can learn to decompose validation tasks automatically. We tried this idea in our ACL 2024 paper and successfully got language models to learn better program decompositions that let the programmers validate code much faster. Looking ahead, I hope models can automatically come up with clever decomposition strategies. For example, breaking theorem validation into lemma validation, or book translation validation into paragraph-level checks. And at last, our final boss, Yang. How do we validate something as complex as research? Decomposition alone will probably not be able to solve this completely, but it will be an important tool in our toolkit. We might decompose research validation into checking individual claims, novelty, and robustness. By building better validation, we hope to build AI systems that are truly geniuses like Albert Einstein. This is the end of the talk, and here are 3 takeaways. First, as AI systems tackle increasingly difficult tasks, validation gets more expensive, and creating a huge challenge we need to solve. Second, decomposition can help us bridge this resource gap and improve language models' ability on hard tasks. Third, looking into the future, we will have plenty of optimization power by default, so validation will be the real bottleneck. Finally, I would like to thank all of my collaborators for contributing to the papers I have presented, and thanks Nicholas Tomlin for providing a lot of useful feedback for my slides. All right, thanks for watching, and feel free to reach out to me if you're interested.